Okay, so let's get started. Um, so in today's tutorial, we'll be start by talking briefly talking about the common problems. So first, assignment 2 has been graded. So please let me know if you have any problems with the grading. And yeah, we'll be coming first talking about some common problems of assignment 2 and assignment 3. And then in today's tutorial, our main topic is data dependency analysis. Okay. So assignment 2, as for assignment 2, so we have discussed how to handle the finals in the case of liveness and anticipated expressions. But we haven't really discussed how to handle finals properly in the case of will be available expressions. So as an example, so in the previously when we discussed as an example, suppose we have a final that is in the format like this. Uh, in the case of liveness and anticipated expressions, we discussed how do we do this sort of redirection or unpacking these finals as incoming values. Whereas in the case of will be available expressions analysis, because it is a forward analysis, so therefore what we should do instead of unpacking it as incoming values, we should sort of merge it as a single node. So what do we mean by this? So as an example, suppose that we have expression 0 plus 2 and expression 1 plus 2. As will be available in all of its predecessors, then we'll be setting expression 2 plus 2 as will be available as well. So this is how we handle finals in the case of will be available expressions. Okay, so in the case of assignment 2, if you didn't handle this final, if you didn't handle this in the will be available expression analysis, you will have an extra early placement in the final basic block. Okay, so this is it. In the case of liveness and anticipated expression, we unpack these finals as its incoming values, whereas in the case of will be available expressions, we merge those incoming values as a single final. So this is how we handle finals in the data flow analysis framework. Any questions before we move on? Okay, good. So as for assignment 3, so just to reiterate, so for assignment 3, we require that the output of your passes should match those obtained from the LVM building pass. And of course, you can certainly refer to the looping environment code motion pass implementation inside our LVM. But one thing that I would like to remind you is that the building path of LVM is really complicated. It's like, if I remember correctly, it's like 3,000 lines of code. And of course, you don't have to implement everything of it. Like what is required for this assignment is much more simpler than the LVM building path, LICM, right? So, but again, so it's okay if you refer to the code of it and learn from its key ideas. Is this clear? Any question? Good. Okay, so if there are no questions, let us go to the tutorial materials that we have for today, which is data dependency analysis. Okay. So in today's tutorial, we'll be discussing about, so our agenda for today's tutorial is as follows. So first we'll be covering 4 basic types of data dependencies. And then after that, we'll be discussing about the data dependencies in the context of arrays and loops. Okay, so what are the 4 forms of data dependencies that we have? So we said so. We have 4 types of data dependencies. That is, we have read after write, whose abbreviation is RAW, which stands for read after write. Write after write, whose abbreviation is WAR. Sorry, write after read, WAR. Write after write, WAW, and read after read, RAR. So let's take a closer look at what those dependencies mean. So in the case of read after write, a minimum example that we have is shown on the slide. So where we have x is equals to a plus b, and c is equal to x plus d. As you can see, so both instructions have been using the same value, x. Apparently, as we can see from the sequence of instructions, we need to compute the value of x before the value of c, right? So this type of dependencies, the read after write dependencies, is also known as true dependency, and it's also known as flow dependency. So those are 2 different names of it. Why is it called true dependency? Because as we will see later, read after write dependency is the only true data dependency, which means that it's impossible for it to be resolved, right? So because as we can see from the sequence of instructions, it is impossible for us to compute the value of c before the value of x, right? And the notation of it is that we'll be stating that the first instruction, S1, is delta true, where this T stands for true, S2. So what can we notice from this notation? Well, our observation is that and the left-hand side of this notation is denoted as the source, and the right-hand side is denoted as sink. So what do we notice? What can we observe from here? Well, our observation is that the left-hand side of the dependency must go before the right-hand side in terms of program order. Okay. This is really important, and we'll keep iterating through this in the later slides, because it is read after write. Okay, and when it comes to the notation, we request that so the left-hand side must always go before the right-hand side. Any question before we go on? Good. So let's talk about the second type of data dependency, which is write after read. So as another example, we have, as shown on the slide, A is equals to x plus b, and x is equals to c plus d. Okay. So this is known as write after read dependency. So you might therefore ask, so okay, so what happens if, let's say, we execute S2 before S1? What will happen in this case? Well, assuming that prior to the execution of S1, let's say X takes on the value X1. In the baseline, what will happen? In the baseline, assuming that X takes on the value X1, then A will take on the value X1 plus B after the execution. Okay. Whereas, so assuming that S2 is executed before S1, what will happen? If S2 is executed before S1, then A will take on the value C plus D plus B rather than X1 plus B, which is therefore incorrect. So this type of dependency is also known as anti-dependency. Okay. And its notation is therefore similar to what we had previously. It's S1 delta A, which stands for anti S2. Okay. Any question here? So as you can see here, once again, the left-hand side, the source, is before the right-hand side, the sink in program order. Question? Okay, and the third type of dependency that we will be discussing about is write after write data dependency. So what happens in the case of write after write? So let's say, once again, we have this simple program that says X is equal to A plus B and X is equal to C plus D. So you might therefore wonder, so what will happen if, let's say, we execute S2 before S1? So assuming that so we execute S2 before S1. So as the program terminates, or instead of saying as the program terminates, as we finish executing those two statements, X takes on the value A plus B rather than C plus D, right? In the baseline, if we assume that so we execute S1, S2 sequentially, X will take on the value C plus D, right, as the program terminates. Whereas if we execute S2 before S1, X will take on the value A plus D, resulting in an inconsistent machine state, which is something that we don't want. So this type of dependency is also known as output dependency. And its notation, similar to everything that we discussed previously, is S2 delta O, which stands for output, S1 delta O S2. And whereas the O stands for output dependency. Okay. So now that we have discussed about write after read, which we call as anti-dependency, and also write after write, which we call as output dependency. But we said so the only true data dependency type is read after write. So why is that? So let us consider those two examples that we have, which is write after read shown as the left-hand side and write after write shown on the right-hand side. Our key observation is that the write after read and write after write are not true data dependency. Why? The reason is because we do not need to execute them in sequence. Compare with what we have okay, so in the case of read after write data dependency, the values are not ready, are not there yet when we try to execute the instruction. Whereas in the case of write after read and write after write, the values are ready. But the reason why we have this data dependencies is simply because of name collision, right? Because as an example, for the example on the left-hand side, the reason why we have this dependency, it's because so we reuse the variable x in S2. And similarly, in the case of write after write, the reason why we have dependency is because so S1 and S2, they are using the same variable, right? Assuming that so we have infinitely number of registers, then the problem of write after read and write after write won't exist at all. Why is that? The reason is because so we could always rename our variables in such a way that they are always outputting to different variables, such that each variable is only assigned once, to avoid this name collision issue. So therefore, from this perspective, write after read and write after write are also called name dependency. Okay, because they are really not true data dependencies. The reason why we have data dependencies is simply because of name collision, right? Because multiple instructions, they are outputting to the same variable. If we can rename variables such that each variable is only assigned once, then we won't have this data dependency problem. Does this sound familiar? Like, have we talked about, have we discussed about similar concepts during the lecture or tutorial? What does this remind you of? Like this technique of resolving name dependencies. Well, not really finals. It's related indeed, but where did we discuss about this notion where every variable is assigned at most once? Yes, exactly. So hopefully you still remember that. So in the case of SSA, we said that so the idea of behind SSA is that so each variable is assigned at most once, right? So this is really similar to how we resolve the name dependencies, which include write after read and write after write. So why we will never have those two data dependencies in the LVM-IR? Right? The reason is because in the case of LVM-IR, S1 will have A is equal to X1 plus B, and S2 will have X2 equals to C plus B, because they are reading and writing to different variables. So this is why we won't have name dependencies. As we see here, as is shown on the slide. Any question? Good. Okay. So now that we do this register renaming, the idea is that in the end, they still so now that we resolve the name dependencies using register renaming, but in the end, they still needs to commit to the same variable x, right? And the idea is that we do execute S2 and S1 out of order. That is, so we allow the machine to execute S2 before S1, or they can be executed in any order. in the registers. But in the end, when they want to commit to memory, we request that they have to do in-order commit, right, to respect the program order. So that is the idea of that is the key idea here. That is, so we do out of order execution, but we do in order commit to respect the program order. Okay, so now that we have discussed about 3 data dependencies type, okay, and the final data dependencies type that we'll be discussing is read after read. As we will see here, we have a simple program here, which says first instruction, A is equals to X plus B. Second instruction, C is equals to X plus D. So you might therefore wonder what happens if, let's say, we execute S2 before S1. What will happen? Well, the answer is nothing happens. Right. It doesn't really matter if we read S2 before S1. So why do we care about read after read data dependencies here? I mean, since it seems as though they didn't affect the program correctness, so why do we care about read after read data dependencies? Well, the reason is because if there are read after read data dependencies, this therefore implies that there are data locality here, right? Because we are reading the same variables. And similarly to all the previous data dependencies that we discussed previously, right? So it is important to note that data dependencies not only represent kind of like the valid, kind of like the program correctness, but also the data locality information, right? So as we discussed, so just to reiterate, the data dependencies not only contain the program correctness information, but also the data locality information for all types of data dependencies, right? Because they are sort of inputting or outputting to the same variable. This sort of represent the data localities that we have in our program, right? So this is why we care about read after read data dependencies as well, even if they won't affect the program correctness. Any question here? Good. And yeah, in contrast to write after write, which we call as output dependency, we denote read after read as input dependency. And its notation is S1 delta I S2, where the I stands for input. Okay, now that we have covered 4 basic data dependencies type, it's time for us to move beyond simple programs to consider data dependencies in the context of arrays and loops. Okay. So we call that we have categorized loop dependencies into two subcategories. So the first is what we call loop independent dependency. As its name suggests, for loop independent dependencies, we have dependency relationship within the same loop iteration. Whereas in the case of loop carried dependencies, we have dependency relationship across different loop iterations. So hopefully this notion is relatively straightforward. What it means, like the difference between loop independent and loop carried dependency. As an example here, so on the left-hand side, we show an example of loop independent dependency, where we have the dependency inside the same loop iteration. Whereas on the right-hand side, we have loop carry dependency. And we'll soon be discussing about what data dependency we have on the right-hand side in the following slide. Okay. Okay, so let us again continue on the previous example, on the examples that we have in the previous slide. And let us unroll this loop. Okay. By unrolling, we mean that we expand this loop at all iterations that we have, starting from iteration 0 up until to iteration 10. So what do we notice here? So our observation is that after the loop has been unrolled, we can clearly see that there is this read after write data dependency. So where is this data dependency? We can see that iteration 1, on iteration 0, we're writing to variable A1. Whereas in iteration 1, we are reading from the value A1. And in iteration 1, we are reading the value, we are writing to the value A2. And in iteration 3, we're reading from the value A2, so on and so forth. And therefore, it is read after write data dependency. Okay. So therefore, we say that this loop therefore satisfies the true data dependency. Recall that read after write is also called as true or float dependency. And therefore, we use the notation as delta subscript 1 superscript t s, where the extra subscript 1 denotes the dependency distance. It shows that the source is always one iteration ahead of the sink in program order. Does anyone have any question here? Good. So now that we have discussed that for the data dependency, we see we have shown for the data dependency analysis, we see that for the left-hand side, the dependency is S delta 1 T S for the left-hand side. So what about the loop that we have on the right-hand side? What do you think shall be the data dependency of it? Are we going to have S delta negative 1 T S? Well, the answer is no. Why is that? So why we cannot have a negative dependence distance? Recall that what we keep iterating is that what we keep mentioning is that for the data dependency, the source must go before the sink in program order, right? So assuming that we write the data dependency like this, which is S delta negative 1 T S, what we are basically stating is that the source goes after the sink in program order, right? Which is therefore incorrect. So what data dependency are we having here on the right-hand side? What do you think? So the correct answer is that in this case, instead of stating that we have a true data dependency of whose distance is -1, we instead say that, so on the right-hand side, we have an anti-dependency, which is right after read of distance 1. Right? As you can see, this notation still respects what we discussed previously, which states that so the source should always go before the seek in program order. Before we move on, may I know whether anyone has any question here? Good. Okay, now that we have discussed about 2 examples on the data dependencies, let's consider the third example that we have, right? Where we are at each iteration, we are reading from the value to I and writing to the value to I plus 1. Is there any data dependency in this bottom loop? Well, the answer is no, right? Because as we can see from this example, at each iteration, the write index is guaranteed to be different from the read index, right? So hence there is no dependency within and across the loop iterations. So let us consider, now that we have discussed about one-dimensional loop structure, it is time for us to move to more multi-dimensional iteration space, right? Consider this example that we have, where we said, so where we have a 2-dimensional loop, I and j, and at each iteration we are doing aij is equals to ai minus 1, j plus 1. Similarly to what we had in the case of 1D loop, right? In the case of 2D loop, we have performed data dependency analysis similar to what we had before. The only difference is that in this case, as you can see from the data dependency notation, our dependency distance also now becomes 2-dimensional, where we have this 1 and minus 1. What we can see from this I minus 1 is that the value written in the iteration ij is always read in iteration I plus 1, j minus 1. Okay, so this is what this 1 minus 1 represents. And similarly, I remember on Piazza, there's a question asked. There seems to be some students confused about the difference between iteration space and data space. Okay. Note that when we are dealing with this dependency analysis and refer those loop indices, we are always referring to the iteration space rather than the data space. So by iteration space, we mean how loops are formed in the program, right? Rather than the data spaces, which is how the data is stored in memory. The reason is because, as you can probably imagine, in the same loop structure, we can have multiple data spaces, right? But they share the same loop structure. So this is why, like on those data dependencies analysis, like no matter the graph that we have previously shown during the lecture, where we have this 2-dimensional graph. Let me just temporarily stop the screen sharing. Where we have this graph shown during the lecture. So on and so forth. or we are data dependency notations that we discussed here. In those two cases, we're always referring to the iteration space, right, which is how the loops are formed. This is really important, not to be messed up with the data space, which is how the data are stored. As an example A. Right. So as we have also seen during, as we also saw during the lecture, you can have a two-dimensional iteration space, but a one-dimensional data space, right? And you can also have a one-dimensional iteration space, but a two-dimensional data space, right? But when doing the data dependencies analysis or locality analysis, we are always referring to the iteration space. Okay, so let's return back to what we have. So what this means is that, okay, so we have discussed about this. So we have discussed about how the notation is only related to the iteration space. So what happens if, let's say our loop body becomes AJI equals to AJ plus 1 and I minus 1 plus 1. Well, the data dependencies that we'll be having is also the same, right? The reason is because the order of dependency distance here is only relates to how the loop nest order and has nothing to do with the array indexing order. Well, the questions that you might have here is that previously we did in the case of 1D loop, we said that so we expect that the data dependency distance should always be positive, right? The reason is because in those cases, we said that the source must always go before the sink in program order. So why in this case, in the case of 2D loop, in this 2D loop, we have a data dependency that is negative, which is -1. Why is this allowed here? Well, the reason is because our key observation is that the iteration ij always go before the I plus 1, j minus 1. Why is that? So the reason is pretty simple. The reason is because, as an example, suppose that we have the iteration variable Suppose that we have this iteration, I1, or 1, 0, where I is equal to 1 and j is equals to 0. So this one always go before two, sorry, this is a bad example. Let's say we have 1, 1. It always go before I is equals to 2 and j is equals to 0 in terms of program order. Even if you have this smaller value for j. Why is that? Well, the reason is clear if we refer to the program, right? Because in the program, we have I as the outer loop and j as the inner loop, right? So this is why in program order, iteration 1, 1 is before iteration 2, 0. It is only the value of I that matters here. So our key observation here is that iteration, again, so iteration ij always go before iteration I plus 1, j minus 1, because it is only the outer loop that matters. So therefore, we have to modify the restrictions that we have previously. That is, so instead of stating that for loop carrier dependencies, the dependency distance must be positive, we said that so the dependency distance has to be lexicographically positive. That is the first non-zero index, the first non-zero dependency distance has to be positive. From the left-hand side, so for the dependency distance from the left to the right, the first non-zero distance must be positive. So this is what we mean by lexicographically positive. Anyone has any question here? Questions? Questions on the dependencies, on the restriction? Good. So let's do a short summary of everything that we discussed today. Okay. So in today's tutorial, we have been discussing about data dependency analysis. Okay. We start by covering 4 basic data dependency types, which include read after write, which is also known as true or flow data dependency. Write after read, which is also known as anti-dependency. Write after write, which is known as output dependency. And read after read, which is known as input data dependency. Okay. And let me stop sharing the screen. As we have discussed, the data dependency information is used for analyzing data dependency. It's useful for 2 reasons. One is we can study the validity of the program transformations that we have, right? The reason is because so no matter what program transformations that we have or we want to implement, those transformations, they will always have to respect the program order to guarantee program correctness. Right? So this is the first reason why we want to study data dependency. That is for the validity of the program transformations. And the second reason is because of the locality. And after that, after we covered 4 basic data dependencies type, we then discussed about loop independent versus loop carrier dependencies, right? Where we said that so loop carrier dependency, in the case of loop carrier dependencies, we have this data dependencies across different loop iterations. And finally, after discuss about the loop carrier dependencies, we finally discuss about this loop iteration dependency distance, where we said that so the dependency distance must always be lexicographically positive. which means that the first, suppose we have this dependency distance vector. The first non-zero value must be positive. Again, the reason is because the source must go before the sink. Where we have the source and the sink. The source must go before the sink in program order. And our observation here is that in the program order, it's only the outermost loop that matters here. Anyone has any questions regarding what we discussed today? Again, so this ordering is only related to the iteration space. So as an example here, suppose we have something like 1, 2, 3, 4, 5. So this one, and we have in iteration space for I, for J, for blah, 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 K, blah, blah, blah. So this I, this one denotes this dependency on I, this 2 denotes the dependency on J, and 3 denotes the dependency on K, so on and so forth. Right. So they have a one-to-one correspondence to the iteration space that we have. It has nothing to do with the indexing order, which is the data space that we have to the arrays. Okay. Now that we have discussed about those data dependencies and the restriction that the dependency distance must be lexicographically positive. So let me ask you a question here. Because we said so, one of the reasons why we want to study data dependency is to study the validity of the transformation, right? So let me ask you a question here. Suppose that we have a loop, let's say I, for I is equals to something, and for J is equal to some other thing. And we have, let's say, 30 body statement here. Assuming that this loop, original loop, has certain dependency here. And further, assuming that we now want to swap the order of J and I here. Under which cases will this swap be not valid? So assuming that the data dependency, the distance vectors that we have in this case, is let's say as in the original loop is as A, B, S. Right. First, let's first ask the question, what might be the sign of A and B? We might have plus, 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 minus, plus 0, 0 plus, cannot, and also 0, 0. Finally, 0, 0. As you could possibly guess, by swapping those two loops, by swapping I and j, we're also swapping the distance vector here, right? So what we'll have in the end is plus, plus, minus, plus, 0, plus, plus, 0, and 0, 0. Which one is not valid here? So this is the one above is before the swapping, right? Because we request that the dependency distance to be lexicographically positive. So that those are the only dependency types that we might have, right? Because we cannot have something like negative plus, because this is not lexicographically positive. So those are the only dependency distance that we might have. So after the swapping, as you could possibly guess by intuition, those are we are sort of flipping B and A here, right? So in the end, we have plus, plus, minus, plus, 0, plus, plus, 0, 0, 0. So which one is not valid here? There's one data dependency that is not valid here. So which one? Right. The reason is because we are no longer having a lexicographically positive dependency distance here. If we do no longer have a lexicographically positive dependency distance, this means that the data dependency has been violated, right? So therefore, to conclude, in the case when the original loop have a dependency distance like this, plus minus, we are not able to perform loop swapping. The reason is because after loop swapping, the distance is the data dependency is violated. Anyone has any question here? How we use data dependency to study the validity of our program. Sorry, the loop transformations. Good. And yeah, that's everything I have for today. Thank you everyone for coming.